Okay. Hello, everyone. Welcome back. I hope that everyone is back. If you have any question from what we were discussing previously, then please let me know. And for a couple of minutes, let me just go over from the beginning what we were discussing. We are discussing trusted computing and attestation protocols. So, trusted computing is it's a mechanism. What trusted computing means is that you want to be able to ensure, you want some mechanism by which you can ensure that the computer is behaving in expected ways. Okay. And the problem that we are looking at right now uh, in is that you are, say, a client of a cloud service, and you want to ensure that the software stack which is running on the remote machine by the cloud provider is actually some particular software stack that you trust. Okay. And so the cloud provider needs to provide a proof of the software stack, that it needs to tell you two informations basically. One is what software stack is running on that remote machine, and then along with this information it will also provide you a proof of that information, which you can then use, and you can verify that indeed that same software stack is actually running on the cloud provider machine. Okay, so this is the problem setting, and it has applications such as you as a client want to ensure that the cloud provider software stack is not running any malicious software. And how are we going to do this? So we are going to do this with attestation protocol. And the attestation protocol is nothing but a challenge response protocol. Okay. So which I just described. And for this in this setting, your cloud provider here is your cloud provider here is the prover, and you, the client, is the verifier. And your cloud provider machine, on your cloud machine, you who is the verifier needs to have a root of trust. And in this setting, since you are attesting the entire software stack, you do not trust the software stack, so you trust only the secure hardware which is present on this machine. So, for example, the TPM. So, you only trust the TPM, and you do not trust any other component on this machine. So, then we discussed that there are these three different forms in which trusted hardware are available nowadays. The first is trusted platform module, which we were discussing about. The other form is Intel SGX, and the next is ARM Trustzone. And the TPM is widely popular and deployed on many machines, and it provides the following capabilities. So it has the following capabilities. First, it is a temper resistant hardware, meaning that even if your cloud provider, say, tries to tamper with the TPM, which is running on the remote machine, by doing a physical attack, then it cannot do so. Okay, so it's temper resistant hardware. And this hardware has a private key embedded inside it, which will be used to generate encrypted data and also generate digital signatures. And this key is embedded inside the hardware by the hardware manufacturer. For example, Intel, ARM, etc. And this private key is even, it's only hardwired inside the hardware and is not even known to the hardware owner. And in this case, the hardware owner is your cloud provider. Even the cloud provider, even though that machine belongs to the cloud provider doesn't know the private key embedded inside the hardware. Then, in correspondence to this private key, there is another key called the public key, which can be used by anybody to verify the digital signatures are indeed was indeed created by the uh, TPM with its own private key. And this is a certified public key which is provided by the manufacturer only when the hardware is purchased. So now the hardware TPM is capable of performing these cryptographic operations such as encryption and digital signatures using the private key. Along with that, it also has a secure storage, which is on the hardware and on board inside it, basically, and it has some on-chip registers also. So the chip basically for the TPM has a secure storage and registers which are uh, not accessible from any other component. Okay. And these registers are called platform configuration register. And currently, although there are about 10 or more registers, we have abstracted this detail, the number of registers. And next, what we are going to say that, okay, we are going to assume that there is only one register, platform configuration, only one PCR register. Then we discuss the API which is provided by this hardware so that we can leverage this hardware for our purpose, such as attestation. So the API which is provided by TPM is called the TPM underscore extend API. This API can be is used by the software such as it is used by the device driver talking to the TPM in your operating system. This API extends the content of the PCR register with the supplied value. So when you call the TPM with some value, say V, then it is going to extend the content of the PCR register, original PCR register value with the supplied value. Now, what does that mean? So we discussed it here that let us say the TPM extend is taking as input a input value V and the PCR register number. Here for simplicity, we are assuming there is say only one PCR register. Then the TPM extend, when you call this TPM extend API, it's going to take this value. It is going to then the functionality it provides is this that it is the current value of the PCR register is taken. It is concatenated with the value that you have provided. Then your hardware is going to compute a SHA-256 over this value, and it is going to store this value now in the PCR register. Okay, and where is this register? This register is on chip register in your TPM, which cannot be accessed from anywhere else. So only the TPM can access. You can just give value to the TPM, and all the TPM is going to do is keep appending the new value with the current value of PCR, and then compute SHA-256 and then store that value into the PCR. So so if the current value in the PCR is U, then after the TPM extend, the value becomes SHA-256 of U extended with V. This what we discussed, and then we also looked at that if you call TPM extend, let's say first with argument x, then with argument y, and then with argument z, like 3 times if you call TPM extend, then in the first step, the value of PCR register, if originally was 0, it will be appended with x, and then it will compute the SHA-256 and store this value in PCR. Next time, the whatever is the content of a PCR register, which is this hash value, will be taken, concatenated with Y, and then SHA-256 hash will be taken over that. Then it again in the step 3, the previous hash value in the PCR will be taken, appended with Z, and then that will be stored. And this is a hash chain. Okay. Uh, and then we said that usually these XYZ values are also hash values which are supplied to the TPM. And then if these are hash values, then if X is equal to SHA of V1, Y is SHA of V2, this is SHA of V3, then if we can replace them here, this string will basically look something like this. And this provides security, even if this PCR final value is, say, even if the TPM gives this final value back to the, say, the user, then the user will not be able to reverse this, because basically the user will not be able to find these values X, Y, Z, or will not be able to generate any input XYZ values which will result into the same SHA-256 value. Now that guarantee is provided by the SHA-256 cryptographic hash function, which provides this property that it cannot be reversed easily. Okay, so that's a cryptographic hash function uh, property, which is saying that even if I give you this hash value, the final hash value, you will not be able to find values X, Y, Z such that you will be able to construct such a sequence of hash chains and thereby have the same hash value. Okay, so that is not possible. And that will form the basis for our security. Now, so given all of this, how does attestation work? So we have the client, aka the verifier, server, aka the prover. The client is going to give a challenge to this server that, hey, uh, what is your software stack? And give me a proof of that. So then the server is going to send a response saying that, okay, here is my software stack and this is the proof. And then you, as the verifier, can take this software stack details and the proof and can verify it. Now, the server must run a software stack here which will support attestation, which should support attestation. Okay. What does that mean? Like basically from time to time, that software should call this TPM extend API with some values. We will look now. So we will look at particular type of attestation now, which is called a trusted boot or secure boot, which which provides a guarantee that your machine has started in a secure state. Okay, what is a secure state here? That your machine was actually started with the correct binaries and all. So now we will look at the machine boot process and that will become clear. So how does a machine boot? So before I go on forward, if you have any question, then please let me know. Okay. So this is how your machine boots. Okay. Your machine, when it starts booting, your hardware starts like starts executing code from this BIOS. Okay, and then the BIOS is going to call the bootloader. So bootloader is the first screen that you will see, and this is also the screen that allows you to configure, like decide which OS you want to run. This bootloader is going to then load the OS image and start the OS. And finally, when your OS has started, then the OS is going to start the applications on your machine. So this is how the machine boots, okay? And the server must declare upfront the versions of the entire boot chain to the client. Okay? The server must say, oh, this is my This is my boot process. This here's my BIOS code. Here's my bootloader. Here's my, oh, not code basically. It will say this is my BIOS. This is my bootloader. This is my OS, which is say version Linux version this. These are my applications, and these are the versions and so on. So the server must declare upfront what versions of the entire boot chain is it going to run, and that it must send to the client. And this is part of your attestation report. Okay, so the attestation report consists of two parts. One is the details of these components, this boot chain, like which binaries are run by by your machine in what order. Of course, any machine boots in this order, but then it needs to say which bootloader version, which OS image and version, etc. is it running. So when the TPM boots, and this is also some another fact basically. So whenever the TPM boots, like whenever your machine boots, so if you shut down your machine and if you start it again, so when that hardware boots, then at that time the PCR registers, the platform configuration registers, are initialized to a known value, which is 0. So the PCR register content is initialized to 0. Okay. Now, Now, how will we attest this boot chain? That is what we are going to look at next. How will we going to generate a proof that this is the boot chain? Not just particularly for this boot chain. What we are going to look at is that how uh, anything which is running your software on your machine, that will be getting recorded. Okay. So when the hardware invokes the BIOS, okay, it measures. So this is a term we use in attestation. So it means that we are going to record something. We are making note of something. Okay. So here it measures the BIOS code. So it's going to measure. So here, look in note that the hardware is invoking the BIOS. Okay, so the hardware is starting execution from BIOS. So the hardware measures the BIOS code. So it is going to measure the BIOS code. What does that mean? It means that it is going to compute a SHA-256 hash of the code of the BIOS. Hardware, before it starts the BIOS, is going to compute a hash of the code of the BIOS, and it is going to invoke the TPM extend with SHA-256 of BIOS. Now, what will this TPM do? What will this TPM extend do? This TPM extend is going to take this value, append it with 0. So 0 will be appended with this value. Now, can you tell me why is it 0 here? Yeah, that is right. Because you are starting your machine. You're starting your machine. You're booting your machine. And whenever the TPM boots, basically whenever your machine starts, uh, and then the PCR is initialized to 0. So your hardware is starting execute. So it has to invoke the BIOS, right, to start the boot process. So the hardware invokes the boot process, sorry, BIOS, but before it does so, it measures the BIOS code. What does measure mean here? It means the hardware is going to compute a hash of the code of the BIOS. Let's say that hash value is SHA-256 of BIOS. So this is the hash. Okay. So BIOS is actually located at a predefined address in your memory. I think the ROM, basically the ROM memory, read-only memory, it's where the BIOS is. And so the hardware knows where is that code and it can compute a hash SHA-256, let's say. So basically there is some mechanism here by which the hardware is doing this. And then the hardware is calling the TPM. The hardware is calling the TPM extend like this API, and it's passing the value SHA-256 of BIOS. Now your TPM, so this call is being made by the hardware, and this operation is happening inside the TPM. Okay, call is being made by the hardware, and the operation is going to happen inside the TPM. So then the TPM is, which of course is also another, which of course is also hardware only, but TPM is another chip. Okay, so here this value is going to be taken, will be taken by TPM, and then it zero will be extended. Zero value, which is the original value in PCR, will be extended with this argument, and then SHA-256 will be computed over this entire concatenated value, and that new value is say V1. Now, where will this V1 value be stored? Where is this value V1 stored? Yes, that's right. So this is stored in the PCR. So the zero value was the original value of PCR, which we concatenated with the argument. We compute the hash, and then the value which is generated V1 is stored in the PCR. Now the BIOS is going to start. Now when the BIOS has finished execution, it is going to start the bootloader. But what will happen is that instead of starting the bootloader code direct but before it does, like before it starts the bootloader code, it will first measure the bootloader code. How will it measure the bootloader code? It will also compute a SHA-256 over the bootloader code. Okay, it measures the bootloader code, means it computes a SHA-256 of the bootloader code. Then it computes the SHA-256 of bootloader code. It invokes this TPM extend. So when it calls this TPM extend with the SHA-256 of bootloader, then this call is being made by BIOS now. Earlier, the call here was made by the hardware. Now this is being made by the BIOS. So hardware has measured the BIOS, computed a hash, sent it to TPM, and then it invoked. So hardware here is not checking anything. Hardware is like, don't even care what BIOS is going to run. It's just going to do something before it starts BIOS. Is that it's like I'm going to compute the hash of BIOS. I'm going to send it to TPM to record it, and then I start the BIOS. Similarly, the BIOS doesn't check what bootloader code is going to be started. It just takes the hash of the bootloader code and it's going to pass that to TPM extend. Now TPM extend here has this value V1 now in the PCR register, not the TPM extend. I mean the TPM is going to have this PCR value V1, which it is going to concatenate with SHA-256 of bootloader. It's, let's say, the new value, and then this it computes a SHA-256 over this entire string value, or some this value basically, and let's say the output is V2. Now this output V2 is stored in PCR. And then in the next step, now the BIOS had started bootloader after that. Now the bootloader is executing, the bootloader executes, and then when it before it passes the control to OS, it is going to measure the OS. So it is going to compute hash of OS and pass it to TPM with TPM extend and call the TPM extend with the hash of OS binary. Now TPM extend is going to pass control to TPM. TPM has PCR value V2, concatenates it with this incoming argument SHA-256 of OS, computes the SHA-256 over the entire value, and then it stores it in PCR. Now PCR content now is V3. And the OS now in turns measure the applications that are going to start. Okay, so if the OS starts, say, Apache server, then the OS is going to take the hash of the Apache server and then it is going to pass that to TPM. If OS then starts, say, the MySQL server, then it is going to take the hash of that MySQL server and then pass it to OS. Sorry, not pass it, and then take the hash over that and pass it to the TPM in the same similar manner. And TPM is just going to take it and then keep appending and then keep computing the SHA-256. So for this particular up to OS, the value which is stored in TPM is say V3. Okay, we are not, let's say we skip the discussion on applications and let's say we have so far measured only till OS and the value in the PCR register, let's say it is V3. So then the value in the PCR at the end of the boot, let's say there are no applications started, so then it will be V3. So then this is actually the proof which is going to be sent back to the client. And it's along with this, the server will also, the cloud provider will also say, okay, this is the bootloader, this is the BIOS, and this is my OS with this version, and etc. These are the details of my software stack, and this is my proof. So if the server booted as it promised, and if the software stack BIOS, bootloader, OS are not corrupted, then the value in the PCR of the server must be V3. Okay, so if this V3 value is, let's say, is the correct value, if your server booted as you promised, let's say this is the true value, okay, which would be generated if the correct binaries were started. So if the server booted as promised, then the value in the PCR must be V3. But if any of these softwares were corrupted, let's say the OS binary was replaced with a malicious binary, or the bootloader was replaced, then if any of them was corrupted, then the value in the PCR will not be equal to V3. So this is a chain of trust that we have built actually. So the hardware, what is this chain of trust? It's like the hardware says that the BIOS SHA is SHA-256 BIOS. BIOS then says that the bootloader SHA is SHA-256 of bootloader, and the bootloader says that the OS code SHA is 256 SHA-256 of OS. And then we have stitched together these values X, Y, and Z here to create a hash chain. Which, like, basically a hash chain is created in the TPM. Now each hash computed by the prior layer. So the hash of one layer here is computed by the layer below. So hardware computes hash of BIOS, BIOS computes hash of bootloader, bootloader computes the hash of OS. So the layer below is computing the hash of the next layer. And at the end, what we have is the root of the trust here. The root, who is the root of trust here? The root is the hardware. Okay, so the root here is hardware. So the hardware, since we trust, we are saying that since the this root of since this chain hash chain was started by the hardware, so if you trust the hardware, then you know that the hardware would have computed hash of BIOS and passed it. So uh, if BIOS were corrupted, let's say, if BIOS was corrupted, then the hash which was passed by the hardware would be a corrupted value, would be a wrong value. Okay, then the V3 PCR value which would be finally generated here would have been wrong, would have not matched V3. But let's say, so hardware here is trusted. This you trust. You do not trust BIOS. And so hardware computes this hash and passes. And if BIOS were, say, corrupted, then the SHA-256 of BIOS would have been a wrong, like different value than the right value. And then this value in PCR would have changed. But if this BIOS is correct, then this value is, say, correct. So the BIOS code is, let's say, it's correct, and this value would be correct. That means if so far this is okay, nobody is correct here. Okay, then the BIOS is going to check the it's not checking, then it is going to measure the bootloader. It's computing the hash of the bootloader. So far, basically, if the hardware is not so hardware is trusted, if the BIOS is not corrupted, then the value would have we would have computed would be V1, which would be correct. Now if the BIOS is not corrupted, but the bootloader is corrupted, then it would pass a wrong hash of the bootloader. Like the hash of the bootloader, when it will take, then that value would not be a good hash value. And then in the second step, V2, which will be computed, will be wrong. And then finally, the value of PCR would be also different from V3. So in this manner, basically, even if one of them is corrupted, the final hash value, which will be recorded in the PCR in the TPM, would be different from V3. And hash for one component is being computed by the prior layer. So that's why we're building root of trust here. So if you trust the so if you're like, if you trust the hardware, then you can establish trust in BIOS. And then by trusting, if the BIOS is correct, then you can trust in you can establish trust in bootloader and so on. And at the end, uh, the root of this chain is the hardware, which is tamper proof. Okay, so is there any question? So we looked at how does a machine boot. This is how your machine is going to boot. First BIOS started, bootloader OS, and then applications. And now we are building a attestation protocol, which is the trusted boot or the secure boot. And for that, the attestation protocol has these steps that we just discussed. Okay, the steps are that the hardware is going to take hash of the BIOS. The hardware is going to take hash of the BIOS and pass it to TPM. BIOS, before starting the bootloader, will take hash of bootloader and pass it to TPM. Bootloader, similarly, when it has to start OS, it's going to take hash of OS and pass it to TPM, and so on. So if in the end, the value which is generated in TPM, you're going to take that value and then you are going to use that as a proof. So this value V3 is here is actually the proof that you have to send to the client. And this value V3 is a hash chain which with the arguments these arguments: SHA-256 of BIOS, SHA-256 of bootloader, SHA-256 of the OS. These were the arguments to the TPM. So then we said that if we trust the hardware, then this then we have been able to establish this chain of trust. So if you trust the hardware, then you can establish trust in BIOS, and then in bootloader, and then in OS, and so on. So importantly, if server declares its software stack to the client, client can simulate the boot process of the server and compute what value should be there in the server's PCR. Okay. So now how will the client do verification? So what we discussed here so far was the proof generation step. Okay, so there are these two components. The prover is going to generate a proof, then the verifier is going to do the verification. So there is like two steps in attestation. Okay, so the first step we covered was how to generate the proof of the software stack. And then we are going to look at how the client is now going to take this proof and verify that it's true or not. So what the uh, client can do, that the server has already provided its software stack information, right? So earlier I mentioned that the attestation report, where was that? Yeah, okay, it was here only. The server must declare upfront the versions of the entire boot chain to the client. Okay, so the server has already declared that this is my boot chain and these are the versions of these different softwares which are running. And along with that, I'm also providing you the value from the TPM, which is this value V3 as a proof. So these two values are sent by the by your cloud provider. Now you do not trust the first value, which is this which is this details of the software stack, but you can trust the second value because and verify that that value is actually generated by the TPM. Okay, by verifying the digital signature over that value. So the second value is the proof. The first value is the I don't know. I think the terminology, but the first value is provided by your by your server is a software stack, and the second value is the proof for that software stack. Then the client can now how will it verify? It can simulate the boot process. It can run the same software stack which the server had run. So in a say new machine, and then it can with the TPM, and then it can try to compute what value should be there in the server's PCR. So how can it compute the same value? Why can it compute the same value? Basically, why is it guaranteed that it will be able to compute the same value? So it will be able to compute the same value because the PCRs always start with value 0. So the PCR will be 0 initially on any machine, and if you're going to start with the same same software stack, which the server has told, then the final value which will be computed in the PCR will be same. And it can also do it like uh, yeah, it so that is because it is just a series of these 256 computations. Okay, so because these are just hash computations, so that's why it will be able to do so. And the starting point is 0, which is also the same for all the TPMs. So is there any question so far? So this is the hash computation which is happening here, and the hash computation is it doesn't require the key. So you give this the value, and then it is going to compute a hash of that value. So the hash is like a table, a very large table where for every value you can compute like there is basically a corresponding hash value. So it's not a cryptographic, it doesn't take a key like a private key. So it's not dependent on that key. So that's why it will be same. So if you compute a SHA-256 of some value on this machine and on any other machine, they will be same. But then it's difficult to brute force over these values, because the input space for SHA-256 can be of any length. So the input can be of any length, and then your value, so the hash which it is generating is of 256 bit for SHA-256. So you can give it any size of input, like you can give it a 1 MB file, it will still compute a hash of size 256, and it doesn't need a key. Yeah. Yeah, thanks for the question. That's a very good question. So then, in short, this is what we discussed. Okay. So this is the client. The first step is the client is going to ask the server. I mean, these are the step in your attestation protocol. The first step is that the client is going to ask the server that give me your PCR after the boot. Then the server is going to give the software stack configuration, and then it is going to give the software stack configuration and the value v3 which is computed in the PCR. The client is going to simulate the boot, compute the boot, and calculate the PCR. It will be computed by the TPM. It is going to get that value and computed value and compare it with the value which is sent by the server. So if the values match, that means the server indeed is using the same software stack. Otherwise, the server is lying. So what can be a problem with this setup so far that we've discussed? Is it possible for the server to use a different software stack and still be able to give a proof v3? Is there any problem you see here? Have you heard about replay attacks? What is the replay attack? Will you be able to do a replay attack here? Okay. So this setup here, I mean, this particular attestation protocol will have a problem. And the problem is called replay attacks. So why the replay attack is what is the replay attack? Replay attack just means that the server is going to send the same value. It's going to reuse the same value. So you computed this value when you started the this server. You, let's say the cloud provider will start the server with the correct configuration. It is going to note down this value, and it knows that if I start the server in this particular order with these versions, then this value is computed. And then it can make a note of this value. Then it will start the server with any software stack, like say a corrupted OS or something. And if the client asks for the value v3, then it is going to give the value v3 that it has computed before. So it can just keep using it again and again without actually computing this value when the client asks for it. So there is no freshness here. Like we don't know whether this value v3 was computed upon my request, or the server had already computed this value v3 before, like sometime before, and then now it is just sending me this value. So that's not so that is there is like we that kind, that is possible basically here. Is that clear? So why, what's replay, what is being replayed here? So here what we have discussed is that the client can ask the server to provide a proof of the software stack. So the client is going to tell the server that give me the PCR value after the boot has happened. And the server is going to say start its software stack, and then it is going to pass the software stack config and the value v3. Now this value v3, what we discussed is the value which would be computed in the PCR if the software stack is computed, let's say, in the correctly, the correct binaries were used. But what may happen is that the server can replay this value. So how does it replay with this? Let's say first you, so how will it that replay it? Basically, that server is going to start in this software stack config, like basically with the correct softwares, it's going to compute this value v3, and then it is going to make a note of this value v3. After that, it can say change the OS binary, or it can start any other softwares or anything. It can do anything basically. But if you ask as a client that what is the software stack you're running, it can still use the same value v3, even though it can be running a different software stack. So here the problem is that we are not taking a note of where the like the server, the client is server is not providing any guarantees to this client that this value was generated right now in response to the client request. So now to enforce that, how do we prevent replay attacks in general? So we prevent the replay attacks in general with nonces. So what's a nonce? Nonce is just a random value. Okay. So what the client is going to do is that when it is now going to send a request to the server, it's going to say here, here is my nonce, which is equal to value r, some random value r, and give me your PCR after the boot. Now what the server is going to do is that it is going to pass this value r to the TPM, and the TPM is asked to produce a quote of the value in its PCR. So then the TPM is going to take the, what the TPM is going to do is that it is going to take the value which is there in its PCR, in this case value v3, and our value is going to going to be concatenated with the v3, and then the TPM is going to compute a digital signature over this. So in public key cryptography, the digital signature is can be computed by doing an encryption of this value with the private key. So it's here E means encryption, TPM, then priv means with the private key of the TPM. So this digital signature will be computed on the value R concatenated with PCR by the TPM, and this is nothing but encryption of this value with the TPM private key. And this is the digital signature. Now, when the server is going to reply back, it is going to send the PCR value v3 along with the digital signature. And also the software stack config. Now, how will the client verify? The client is again going to simulate the boot, get the value of PCR, and then it is going to check for a match. For that, it is going to take this it is going to take this PCR value and check for a match. So if the matches, then it is going to verify the digital signature. Now, to verify the digital signature, this is this encryption like cipher text, which was generated with the private key of the TPM. It is going to take the public key of the TPM, which is available to anyone because it's public. So it is going to take this public key of the TPM, and then it is going to decrypt this digital signature with the TPM public key. And when it is going to decrypt this, it will get these two values are concatenated with PCR. Then if the decryption happens correctly, that shows that this value was indeed encrypted by the TPM. That means it can then verify that it is indeed the value of R which it had passed in step 1. Second, it can check that this is the PCR value here is matching with this PCR value. And in this manner, it will be able to verify the server is not replaying the value. So this is the attestation protocol for trusted boot. And if you have any question, then please let me know. Yeah, the server sending a recorded value of V would be the uh, replay attack. That's right. Now here, so we have covered secure boot. Do you have any questions, or is everything clear? Hmm. Okay, so let me just ask, who is what is the root of trust here? What is the root of trust in secure boot? So in this attestation protocol that we just looked at, what is this? No, 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 no. So the knowns we are using here to prevent the replay attack, to guarantee freshness of this value, PCR value, which is being sent back. But I'm asking, what is the root of trust? So we discussed previously, uh, right? So we were discussing that since we are, the problem here is that we want to that the problem here is that, let's say you are the client and you do not trust your cloud provider, and you want the cloud provider to provide you a attestation of the software stack which is running on the remote machine. So basically provide a proof of the software stack. Now, you do not trust any softwares on this machine, and you, client, you only trust the trusted hardware on this machine, such as TPM, because the TPM is has provides guarantees such as it is temper registered and it can do encryption decryption with the private key which is embedded inside the hardware. So you trust only the hardware which is present on this machine here, and you do not trust any software stack. So your root of trust. So the root of trust here is the hardware. Is that clear? The hardware is always the root of trust. So actually the hardware is the lowest layer basically, which can be the root of trust. And so in the computer system, this is the lowest layer. So hardware can be the root of trust, but then there can be other component also. If you trust the OS, then that can also serve as a root of trust. But that depends on your assumptions actually. For this particular problem here, we do not trust any software, any software. So we are saying, okay, we are going to trust only the hardware. But uh, if you have some other problem setting where you can say you trust, say the either the hypervisor or the operating system, then that can also serve as a root of trust. So any entity, uh, hardware or software both, can serve as a root of trust, but here in this particular setting we trust only the hardware because we have to attest the entire software stack, so we do not trust any software. Is that clear? Okay, thanks. Now let me just, what is a attestation protocol? So what's attestation? Or maybe let me ask. Yeah. Any other answers? Yes. So attestation protocol is a set of messages which are exchanged between the remote machine and say our machine, where remote machine is the prover and your machine is the verifier. And the goal is to verify the integrity of some is to verify some property. Okay. The goal of the this message exchange is to verify some property. And the property here in this case was to verify that that your cloud provider remote machine is using a particular software stack. So that was the attestation. Now, with so what we discussed was the secure boot, particularly like secure boot attestation protocol. So the question is, uh, will you be able to detect if a malicious OS is started with secure boot attestation? Yes. So because we are computing this value in the PCR register, and to compute this value, these different parts like hardware, BIOS, bootloader, etc., they're passing the hash of the next component in the boot chain, and then this value V3 was computed. And if this value V3 is changed, so when this uh, sorry, when the OS binary will be replaced with the with this malicious OS binary, so the value of PCR will be changed. It will no longer be V3, and then therefore the cloud provider will not be able to prove that this is the correct. Uh, will not be able to prove that it is running the correct OS binary. Now, no. Basically, let's say once the secure boot attestation process has finished, okay, if the if the cloud provider modifies this OS binary or starts a malicious process, will the client be able to find out? So you have, with the secure boot attestation process that we saw, uh, the, the cloud provider has sent this value V3 saying that, okay, I started with this configuration and these are the applications which are running on the machine, and I'm guaranteeing this, and here is my value. So take this value, and then then you're you take you get that value, and then you verified and you're satisfied, okay, this is the software stack which is running. Now, once this process is finished, if the cloud provider can the cloud provider modify the OS binary and start a malicious process, and will the client be able to find out? So it's like the known, but every time for that you will have to then ask it for, okay. So I think I have not framed my question correctly. um yeah, so so nonce will of course be able to stop this if the if you restart the process. So what is nonce? the nonce basically what was the it was to stop the replay attack. So let's say the client asks the OS that, hey, you tell give me a proof of the software stack which is running. Okay, and here is my nonce. So the nonce provides the freshness guarantee that, let's say it's giving a proof, then that is a fresh proof generated upon my request. But what I'm asking is that, let's say the cloud provider started with this particular software stack, okay, and then it gave you the value v3 with nonce as well. But later, after secure the boot has happened, and you as the client have verified the boot process has started correctly, you gave your process, you give your computation to the cloud, and the cloud provider starts your computation. Now, is it possible for the cloud to change the OS binary or to start a malicious process? And if it does so, will you be able to detect it? It can verify the digital signatures. Yeah, the digital signature is uh, was useful actually. Mm. Yeah, so the digital signature over this value of nonce plus the PCR was giving us the guarantee that this value is indeed generated by the TPM upon request, and the request had this ID R. Okay. And this question, I think it's a bit confusing, so I'm going to explain it. Is I'm asking is that, let's say this boot process has happened, and the server was the client had sent that request to server, and then give me your PCR after boot. Here is the nonce, and the server then starts the machine in this for particular software stack, and everything it does everything as you asked. So it's not trying to cheat actually. It's doing exactly what you have asked it to do. It's starting the right software stack. It's giving you the right value of the PCR with the right digital signature and everything. So till step 4 everything is good, you are able to simulate the boot, you're going to verify the value, it matched and everything is good. Now you as a client, you have verified that what the server is doing, right? Like basically what software stack is running on the server. And now you're like, okay, let me give you my computation. So you're going to give your computation to server, and then the server has your code and data, so it can it can run that code with the data you provided. Now after this step 4, I mean after the step 4, when you have already verified and when you have sent your code and data for say execution on the server, what I'm saying is that now the server can start some new application, say a malicious application, a malware application, which can try to steal your code and data which is running in another process. And there is nothing here which will stop the server from doing that, because the secure boot attestation was only attesting that until this that your server is going to start in a basically in a expected way in that correct state. So this secure boot only gave you the guarantee that your server started in the correct way with the correct software stacks. But later what server does, or whether it get infected with some malware virus or something, that is beyond the secure boot attestation. Okay, so it was just a static attestation. I mean, static means that it was just done one time initially, and when the server was booting, and it was used to check the integrity of these uh, things like the OS is correctly started and all. But after that, the OS can get infected with a virus, and then it can try to steal the data of code and data that you have provided to the server. Is that clear? Yes. So if you want to be able to detect those kind of attack, then you will have to continuously monitor the runtime state of the OS and other critical components, as you've just said. So that's absolutely right. So secure boot is only providing you the guarantee that your machine was started in a secure state with the correct software binary. But once it has started, as a client, you have verified that it started correctly. After that, if it gets infected with a virus or your cloud provider purposefully changes the OS or starts a malware application, that is beyond the secure boot attestation protocol. For that, you will need additional mechanisms, such as you will have to continuously monitor the runtime state of the OS or other applications, or you may have to move your critical code and software, so code and data that you're providing to the so your code and data that you're providing to the server, you that should the computation should happen in a secure place, and such as the other two secure hardwares that are there. So there are these two other secure hardware, SGX and Trustzone, which have this capability that you can run your computations inside a secure hardware. So that's what we are going to look next. And so that's basically, I hope that you have so far it's clear that we started basically with what is trusted computing. We looked at the trusted uh, we looked at the attestation protocol. Then we said there are these three kinds of trusted hardwares, TPM, SGX, and Trustzone. We looked at like what features TPM provides and how we can leverage those features to do to like to implement a secure boot attestation protocol. But then we discussed just now that that is not enough, because although your system started in this correct state, which you have verified with secure boot attestation protocol, the OS can get infected later, or the OS might be replaced with a malicious binary, and your cloud provider can start, say, another malicious application on the server to learn your code and data. So many things are possible afterwards. So that's why we need to have now more mechanisms to prevent the code and data that you're sending to the cloud provider. And that's the motivation for the next part, which we are going to look next. So the TEE, like these next trusted hardwares that we are going to look at now. So we are going to start with like what is a trusted execution environment, and then we are going to look at ARM Trustzone. So, but before I do that, mm, let's if you have any question with what we discussed here till here, let me know in the chat box. And otherwise, let's take a 10-minute break here, and let's meet at 3:40, and then we will start with TE and ARM Trustzone. If you have a question, then please feel free to ask. Okay, so hello everyone. I hope everyone is back. And so now we are going to look at trusted execution environments. And these slides are from Professor Chester Ribeiro from IT Madras, and I've used his slides previously also. So what we are going to look at is trusted execution environments. And this is the setting that we are working in, right? That we just discussed. So we now look at how to run sensitive code in an untrusted environment. So this is what we were discussing. So you as a client, you are providing your code and data, which is sensitive, and you are giving it to the untrusted environment, which is your cloud service provider. So now you do not trust this system, okay? And so how can you ensure that your uh, application, your so that is one basically one application can be for this, okay? So that can be one of the settings, but this is also applicable even when you have your own machine, like your phone or your mobile or even your own machine. So here we now look at how to run a sensitive code inside a untrusted environment. So basically, we do not trust, of course, the other applications which are running in this system, and we even do not trust the operating system. And let's say the attacker can even probe the hardware. So this is our basically this is our threat model. Okay, that we do not trust the applications. The applications are untrusted, OS is untrusted, and the attacker can probe the hardware. And so, and what do you want to protect? You want to protect the code and data of the sensitive application. Uh, that and you want that the data privacy and integrity is maintained, so the data does not, your code and data is not getting leaked, or it is not getting modified by any other application, OS, or even the attacker who can directly probe the hardware. So this is possible with the help of trusted execution environments. So these trusted execution environment provides a segregated area where you can, which is not accessible from any other part, including your operating system or other applications which are running here. Okay, so it provides a segregated environment where if you run this application, if you run your sensitive program here, then its data, code, or its computation cannot be uh, read, or it cannot be modified from anywhere else in your system, including the hardware. Okay, so which we are going to uh, look at now. So why does this problem exist, that if you run this sensitive application uh, in your system, then what's the problem basically? So the problem exists because of the ring architecture. So so as we know that the operating system, so basically in your x86 has these four protection rings. And similarly, your ARM also has the execution levels, four execution level. Now, what are these protection rings or execution levels? These are the basically these are privilege rings or privilege modes in which your processor can run. Okay, so there are these four rings in your x86: ring 0, ring 1, ring 2, ring 3, where ring 0 is the most privileged ring. or level, and ring 3 is the least privileged level. Okay, and these are different protection rings, basically protection rings. And these, so when you run a software in ring 0, that software will run as the privileged software. So basically, that software is the most privileged software, and it can say access any memory in your system, or do any, or it can change any registers, or it can run any instructions. And your if you run a software in ring 3, that is the unprivileged software. Basically, that software is running with the least privileges. So here, so your in this ring architecture, basically your OS runs in ring 0. So your OS kernel runs in the ring 0, and your applications run in the ring 3. Okay. So imagine that, I hope you are able to follow that your hardware, such as an Intel hardware, provides these 3 rings, or these 3 modes in which your processor, these 3 different execution levels in which your processor can run. Okay, and your processor, if it is running in ring 0, then the software which is running there, that is the privileged software. And when your applications are running, then your uh, processor is running in ring 3, that is the unprivileged layer. So these are the protection rings, and the goal of these protection rings is to isolate the operating system from the applications. So your OS runs in ring 0, and your applications run in ring 3. So all of these applications run in ring 3, and your OS runs in ring 0. And because of this ring architecture, because of these ring, uh, like how this ring exception, because of these execution levels or rings, protection rings, your applications cannot are so the applications cannot access the OS. So it cannot access the OS, or it cannot even access the hardware directly, because only the privileged software can do that. However, since the OS is running as a privileged software, it can access the applications and any memory that they have, or anything that they are doing. So the OS has access to everything in your machine. It's running in ring 0. It's the most privileged software which is running, and it has access to all the applications. It has access down on to all the hardwares, uh, like peripherals and CPU, etc. So this is like a normally what would happen. And then the OS enables the isolation between the different applications which are running in your machine. For example, Chrome is running, Teams is running. So they are also isolated from each other by the OS. And to do so, the OS uses memory virtualization and paging. So then the OS is going to allocate some memory to each process. It virtualizes the memory space of the processes and isolate them from each other. So each process can only access the memory that belongs to it. And since the process is anyways running in ring 3, it cannot access any hardware directly. And it cannot access any memory which doesn't belong to it. So the applications are isolated from each other, and the applications are isolated from the OS, and only the OS can access the application's memory. The applications cannot access the OS code or data. If they want to use any service of the OS, then they can do a system call. Okay. So they can perform a system call, and then the OS is going to check what the application is asking it to do. but but it cannot read the OS code or data. So that's the ring architecture. So this protection, basically this isolation, is provided with the ring architecture in Intel. And similar ring architecture, but similar protection modes exist in ARM, and those are called execution levels. And there are also four execution levels in ARM, EL0 to EL3, and here the rings are ring 0 to ring 3. So OS is running in ring 0, applications running in ring 3, and usually the two rings which are, they are not used. Okay, and those two rings are usually not used, and uh, these are the rings which are used here. So this is how the applications are isolated and the OS is isolated. But what is the problem here? So the problem here is that this isolation is provided with by the OS. What if there is a malicious application on your machine, and this malicious application is able to say hijack the control in your OS? So as we were seeing at these memory exploits, which were like the C and C++ vulnerabilities. And as you all know that your operating system is also written in C, C++ languages. And it of course can have these memory vulnerabilities such as buffer overflow or format strings, and there are other vulnerabilities also. So it is also a software that are written in memory unsafe language. It can have these vulnerabilities which can be exploited by a malicious application. It can try to send, when it is say making a system call, it can pass some it can pass some value to the system call so as to hijack the control of the OS, and it can try to take over the OS. So if the OS is corrupted, and if it is able to inject a code in the OS, and those kind of attacks, so when you add a malicious code in the OS, that's usually called a rootkit. Okay, so the root, if it is able to add a malicious code into the OS, then basically this application can try to escalate its privileges and can try to run as a say a privileged process. And if this happens, if the OS is corrupted, then since the OS is the privileged software and it can access anything on your machine, so basically the entire your entire system is corrupted. So if OS is corrupted, your entire system is corrupted. And it takes only one malicious application and only say one exploit to gain inside the operating system to gain full privileges of your machine, and then say tamper with the OS and other applications on your machine. So that is why it is not enough. And further, there can be invasive attacks also. So this was like attack on the OS. And of course, there can be other kind of attacks to such as the invasive attack, basically the physical attacks. So the different components in your computer, such as the CPU, memory, input, output units, they communicate with each other over the system buses, data bus, address bus, control bus. Okay, and uh, the attacker can add probes in your, can open your like they can there. So it's possible to do a physical attack. The attacker can add probe in your chip and can try to learn the values which are being passed on in these buses. And if it is able to get these values which are being passed in the buses, then it can basically try to find out that exactly what is your machine doing. So such attacks have been shown. So it has been shown that such attacks are possible. Okay. So this is the motivation for using a trusted execution environment. So, a trusted execution environment will guarantee you confidentiality and integrity even when the OS is compromised. Okay. And it's basically that it also provides, it's also usually enabled by a trusted hardware such as the SGX or the ARM Trustzone, which provides this temper proof guarantees. Okay, so it achieves confidentiality and integrity. So even if your OS is compromised, but if you're running your application inside the trusted execution environment, then even the most privileged software in the previous case, OS, will not be able to tamper with your process. So it will not be able to learn the content like the code or the data, and it will not be able to modify the code, data, etc. of your process if it's running inside a trusted execution environment. So trusted execution environment basically provides a isolated region, a isolated environment to run your process, which is enabled by the trusted hardwares, and it is secure even in the presence of the even when your OS is compromised. So it's enabled by these two trusted hardware platforms, ARM Trustzone and Intel SGX. And Intel SGX basically provides enclaves. So, so, so it works something like this, that when your process code and data is stored on the RAM, it is going to be stored in encrypted form, and then you can, when you make a call to the enclaves. So enclave is like a protected memory region inside your process, and when you pass these encrypted so this enclave basically reads this encrypted code and data from the memory and decrypts it inside the enclave only and execute. So uh, inside this protected memory region only, the code and data is decrypted and then it is executed, but outside it, the any software or hardware would not be able to see. But what we are going to discuss in detail is ARM Trustzone today, which and see how it can be leveraged to enable trusted execution environment. So now coming to ARM Trustzone, but before I go on with ARM Trustzone, is there any question related to trusted execution environment? So maybe I can just quickly ask some questions. Um, I don't know. Yeah. How many protection rings are there in your x86 processor? May I think it's how many protection rings are there in your Intel processor? Yeah, so yes. So there are these four rings, but not all of them are used. So can you tell me where in which ring is your OS running? Yes, so your OS runs in ring 0. And in which ring does your applications run? Yes, right. So your applications are running in ring 3, your OS is running in ring 0. And ring 0 is the most privileged ring, and ring 3 is the most unprivileged ring. And after that, So, because of this ring architecture, your OS is the privileged software and it can access anything on your system. It can access all the applications, but the applications cannot access the OS code data or the other hardware on your system. And how does who enforces the isolation between the application? Yeah, so the OS with memory virtualization is sorry about this. So the OS with memory virtualization here. Okay, I think everything is open. See? Mm. So your OS uses memory virtualization, implements memory virtualization to uh, isolate the processes from each other. Okay, and if the OS gets corrupted, if it is then basically if you are running your sensitive application here, then the attacker can learn the content of this application. So now coming to ARM Trustzone. So ARM Trustzone is the trusted hardware from ARM, and so this ARM. So let's talk about this ARM system on chip. So this means that different components are all fabricated on the same chip basically. So this chip has the main processor, which has the core Cortex A8, the cache L2 cache. It has the interrupt controller along with these modems, and here is your L3 cache, and here is your DRAM, and this is your memory controller, uh, and here is your boot ROM, okay, where your BIOS is going to be stored. So these are the different components, different modules, and all of the modules are actually uh, like all of these modules are fabricated on the same chip, and this is called a system on chip. So everything is present on the same chip, and that's why it's called system on chip. In earlier times, these different components were used to be separate chips, and then they would be connected with each other. But because of that design, the it would lead to actually a larger setup, and that would be like it would be large basically. But now because of system on chip, because the different modules can be fabricated on the same chip, the chips have become smaller, and that's why your mobile devices have also become smaller. Okay, so that's nothing related to the trust zone, but we just see that all of these components are basically present on this same chip only. Okay. Now in the ARM trust zone, the main idea is that, so this is the diagram which I'm going to refer to again and again. Okay. So your ARM trust zone hardware basically divides your execution, processor execution uh, environment into these two. Okay. So it's enables these two execution environment. One is called the normal world, and it is also called by another name called rich execution environment. The other is called the secure world, also called the trusted execution environment, or TEE for short. So your trust zone enables these two uh, environments: normal world, secure world. And your hardware and software is also partitioned into these normal and secure world. Okay, so your hardware and software is also going to be partitioned into these different worlds. Here you can see in this picture is actually only the software components. So in the normal world is now what we discussed here, this part. So all of this part, here, it's now going to be run in the normal world. So you can map this figure that you're seeing here, application, malicious application, and this OS. You can just map it right here in the normal world. So your applications are running here and your OS is running here. So that you can put here. So that's where your normal like Linux OS is running here in the normal world privileged mode, and your applications are going to be run in the normal world user mode. So then what is running in the secure world? Your secure world has three layers basically. The first, the most unprivileged layer is the secure world user mode, where applications are going to run. Okay, and the next layer is the secure world privileged mode, where your secure world operating system is going to run to manage these applications. And then there is also a software called monitor and secure monitor basically. And this software is also there. Now, but there are three layers now. Okay, so these are the three layers, and so these three layers will run on different execution levels. Okay, there are three layers and they all run on different execution levels. One second. So your one second, I'll be showing you another picture. I think that will be better. So I hope this is visible. Uh, so this is your normal world. Okay, actually, yeah, you can ignore these two parts. Okay, so this is your ARM trust zone, and these are your this is your normal world, and this is your secure world, and this is your secure monitor. So I'm going to use like show you here, because here you can also see the execution levels. Okay, EL, these are the rings. So similar to Intel, ARM also has these protection levels, but they are called EL, execution levels in ARM, and they are EL0 to EL3. And it's also reversed here, because in ARM, EL0 is the most unprivileged layer, EL3 is the most privileged layer. So your secure monitor is going to run in the most privileged layer, EL3. So it runs in the execution level 3. Your OS in both the worlds, they are going to run in EL1, execution level 1, and then your applications are running in EL0. Okay, so we have differentiated about between these different layers with the execution levels. Okay, so this is your execution level 0, where your applications will be running in both the normal world and the secure world. EL1, your OSs are running in both normal and secure world, and EL3 is where secure monitor is running. So this is your ARM trust zone, and in terms of the protection ring. Yeah. So that's how these will be placed in layers. And now, now that's how the software layers, softwares are placed in the normal world and the secure world. And then, uh, what is there is that, okay, a single hardware processor time sliced between the secure and the normal world. Now, but how will you run this normal world and secure world? So it's like that if you, so the single processor will be running these different worlds in a time sliced manner. That what does that mean is that at a particular point of time, your processor can be either in the normal world or in the secure world. Okay. So at a particular point of time, your your processor can be either in the normal world or the secure world. And when it will be running in the normal world, then the OS which will be running will the normal OS, applications which will be running will the normal application. And when your processor switches to the secure world, basically running the secure world, then the applications running will be secure applications, OS running will be secure OS, and then there is also this secure monitor. So your softwares are partitioned into these two worlds, normal world and the secure world. And your hardware is also partitioned, and we'll see in next few slides how. And when your hardware is so basically your hardware processor is time sliced, and at a time it can run only in either the normal world or the secure world. Now, the secure world provides an execution environment that supports confidentiality and integrity, meaning that it can prevent software attacks, and it can also so it supports confidentiality and integrity. So basically, if you are running your application inside this secure world, then if that application, so that application's data and compute will be protected, and if and any application running in the normal world and even the privileged OS running here cannot find the data, cannot have access to the data of the application running in secure world. So it cannot access the data of this application running in the secure world. So it cannot basically even like hijack the control flow if this application running. It cannot do any attack on this side. So that's the guarantee which your ARM Trust Zone is providing. Although I must say that ARM Trust Zone, there has been attacks on ARM Trust Zone as well, and of course that's like it's not like completely secure. So there have been attacks even on on the ARM Trust Zone, but this is the what it provides. Mm, and is there any question? Mm. So maybe I can ask quickly. So you have these now how many no how many rings are used in this yeah, so very good question. Yes, so there are two OSs and there'll be two bootings that will happen. Once the secure OS will be booted, and then the normal OS will be booted. So basically, how that happens is this, that first your secure monitor will be started. Okay, your secure monitor is the most privileged software running here. It is running in EL3. The secure monitor is going to then pass control to the secure OS. The secure OS is going to start, and when it has booted up and it has set up everything, and then it is going to pass control. It is going to basically send a then the monitor is going to send a command, like basically pass control. What do I mean by pass control is basically then it is going to uh, ask the processor to switch to normal world and start start with the boot up of the normal OS. So that I will come to back again in the end. Hopefully, then it will become more clear if it's not clear now. But yes, there are two OSs and they will be booted up separately. So how many rings are being used here now? If you want to enable this ARM Trust Zone, TEE, how many rings are being used? Yes. So three rings are being used. And why do you need three rings? Why do you need three rings? Exactly. Yeah, so you need one more ring here for the monitor because you want to. So it's like you cannot run. So earlier you had only these two privilege levels. You had like one unprivileged level for your application and the privileged level for your OS. Now, of course, your applications are running here. You cannot put them with your OS, right? And you cannot put the OS with your monitor also because you do not trust the OS. Even this OS you do not want to put with the monitor. Okay, so you can't put applications with the OS, so the applications will be running in the most unprivileged EL0. Your OS is going to be cannot be run with the monitor because we monitor has to be more uh, privileged than your OSs here. And why is it more privileged? That because it has some more privileged operations that only the monitor can do. So there are some more privileged operations that even these OSs cannot do. Okay, earlier your operating system had the capability to do anything. It could access any memory, it could access any registers, but that is no longer true. So your OSs are no longer cannot they so they these operating systems now cannot do everything on your machine. So there are now some operations which can only be done by the monitor, and we need three different layers, three different execution levels for them because we want to isolate them. We want to isolate the applications from the OS, and the we want to isolate the monitor from these OSs. So that's why we are using three different layers. And so just to emphasize, I would say that you should like make a note of this, that at a time in your processor can either be in the normal world or in the secure world. It cannot be in the both worlds. So if your processor is running in the normal world, then it basically what is running on the processor is the normal applications and the normal OS, and it will have to switch from the normal world to the secure world. So when it makes a switch, then all of this is gone. This is no longer present on your processor, and then this is the state, this is what your processor will be running. It will be running the secure OS, the secure applications, and the monitor. So at a time, your processor can be either in the normal world or the secure world. Means at a time it can either be running the normal OS or the secure OS. So it's time sliced, and your softwares are partitioned into the normal and the secure worlds in in such a manner, and you have these softwares on different ring in different execution levels so that they are isolated from each other. Now, what is this? So we will come to the more details next. But what can you achieve with the trust zone? So what can you achieve with trust zone? So an application of trust zone can be something like this, that consider that you are running a, like, since like ARM Trust Zone actually is widely deployed in mobile devices. So we have here taken an example of a mobile. Let's say you have on your mobile an application armory, and your application uh, is running on top of the rich operating system. Rich operating system is another word used here for the normal world OS. Okay, why is it called a rich OS? It's called rich OS because it's the normal Linux OS which has these mm, like so many features which so it's a large code base and it has diverse features. So that's why it's called a rich OS, and your application is running on top of the rich OS. Now, if this application wants to talk to the trusted world, which is also called the secure world, which is also called the TEE, then this application is going to use the TEE SDK. The trusted execution environment provides basically some APIs for your rich world, like basically your a normal world to talk to the secure world. So it provides some APIs. And you what your in this particular example, what we are doing is that, let's say that your this application is asking the user to enter a pin. So when you click on the button enter pin, what happens is that the code is going to call the TE SDK. So, and it is going to pass the control to the TE. Pass the control to the TE means what? That your world will be switched. Now your processor will switch to the secure world. It will start the secure OS and the secure application. So let's say that to correspondingly a new application will be started in your secure world, and let's say this is the trusted application. Okay, and we will see example of these client application and trusted application in the demo. Okay, so your trusted application will be started now. So here with trust zone, what we have configured the system such that the trusted application can access the it can access the display driver. And this trusted application will when this trusted application is invoked, at that time this trusted application has so whatever input you enter on this display, on your display, that is only accessible by this trusted application. So the display driver is going to take that and pass that input to your trusted application. Okay, so that is your system configuration. So system has been configured such that, so if when you enter in something on your display, so how will it work is like with with the interrupts. So when you enter something, when your user enters something, that like causes an interrupt, right? And now when the interrupt happens, then your monitor, your secure monitor is going to decide like whom to pass this interrupt. So the monitor will pass the interrupt to the your trusted application. So in this manner, when your user is entering the pin, basically that pin will be passed only directly to the trusted application, and it will not be available to this user application running in the normal world side. And then the trusted application can verify that whether the pin is correct or not, or like any other operation, whatever the operation was required. So this can do that operation on the behalf of armory application, and this provides us guarantees that when the user is going to enter the pin, that pin is not accessible by this application. When the pin is entered, it is directly read by the trusted application, and trusted application here has stored the original value of the pin, and then it can do a match, and it can check whether it is okay or not, and then it can just send back the result whether the pin matched or not. So this can be a application in your this can be one of the application which can be used, say, in your payment apps. So when you want to enter your, say, UPI pin or something, so you do not want that UPI pin to be read by some other application or even that same application, right? You are entering your UPI pin, you do not want it to be uh, leaked, right? So so this form, like, so ARM Trust Zone in such cases enables you to write your applications in such a manner. So when you will be clicking on this change, say enter pin, then it is going to pass the control to the TEE. The TEE will start a trusted application, and that application will directly read the input from the screen, from the display, and it is going to do the matching, and your application on the normal world will never come to know what the pin was, and which protects the integrity of the pin which you are entering. So, is that okay? Is this setup clear? Do you have any question? Is there any step which is not clear in this example? Okay, so I hope it's clear and it makes sense. So I will move on. And now I will tell you that how can you switch from one world to the other. Okay, so there are these two different worlds: normal world, secure world. Normal world is where your originally your app, this armory application was running. Okay, and uh, when you have to enter your pin, when let's say it's a payment application, and when you have to enter your pin for to verify a transaction, then it is going to switch to the secure world, and then the secure world will start a trusted application. The trusted application is going to basically uh, is going to start, and then it is going to read the value from the display. So at a time, note that only you can either be running in the normal, so not you, I mean, at a time the processor can be either in the normal world or in the secure world, but not both. So to switch from one world to the other, uh, so uh, so this is switching worlds, and to switch from one world to the other, they that is actually enabled by the monitor. So that's something which what the monitor is doing. So the monitor is the software here which is enabling the switch from normal world to secure world and vice versa. And your basically any other software cannot do it, only the monitor can do it. The only the monitor can switch worlds. Okay, so that's why it has some operation, as I was saying. As I was saying earlier, that it has an operation which only it is allowed to do, that is switch between these two words. Okay, and that should not be allowed from any other place. Now, so to enable this switch between the words, there is a new mode which is the monitor mode, that is the execution level 3, that is invoked during switching words. Now, how does the mode switching happen? So for this, ARM Trustzone has uses a different instruction, and like basically uses a new instruction which is part of the ARM ISA, which is the secure monitor called, and in short SMC instruction. And the instruction is this only, actually, if it's like it's this instruction only, SMC, and then it just like hash 0 or something. So if this is the instruction, and you can see it in the code as well. So this is the instruction, and when this instruction is executed, at that time this instruction causes a exception. So this instruction is going to cause a exception, and that exception is caught by your monitor. So we'll just come to it. And mode switching can also happen. So mode switching can be triggered either by executing this SMC instruction, or the mode switching can happen on hardware interrupts. Uh, and so we'll see that, I think, also in a bit. So remember this. Afterwards, the monitor mode, what happens inside the monitor mode? So because you are switching from one world to the other world, as you have to do when in a normal, when your OS and applications are running, when your applications are running and if your OS is running, if you switch from the user mode to the kernel mode. So if you recall that the operating system saves the context of the process which was running, and then it switches to the kernel mode. And then if it wants to, and then when it has to return back to the user mode, it is going to restore the context of the process which was running. Similarly here, the monitor is going to save the state of the current world, and it is going to restore the state of the world being switched to. And this restoration is done by return from exception. Okay, so the monitor mode basically can be so you can reach the monitor only by exceptions. So one is that you can do it by executing this SMC instruction, which also causes an exception. Or maybe when you were executing in the normal world, then some exception happened, and that exception will pass the control to the monitor. So then monitor will start executing. Now, how do you distinguish between these two words? So we distinguish between the different layers, like the OS layer, the monitor layer, and the application layers. We are distinguishing between these different layers with exception levels. Exception level 0, 1, 2, and 3, so on. But how do you distinguish between these two different worlds? How would your processor know that which world it is running in? So it has to have some state, right? It has to have some state to keep that information, which mode is it running in right now? Not mode, which world is it running in right now? So that's for that your processor has a bit, like it's a bit in a configuration register. This bit is called the NS bit, non-secure bit. It's in the configuration register, and it indicates whether the processor is operating in the secure mode or the normal mode. So if the bit is set to 1, that means non-secure. So your processor is running in the normal world or non-secure mode. And can you now tell me who can set this bit? Who can change this bit? Yeah, that is absolutely correct. So your monitor can change, only your monitor can change this NS bit. Okay. Okay. Let me first. Okay. Yeah. So, uh, let me ask you more questions. So, as a programmer, if you want to switch from one mode to the other mode, from the normal world to the other world, then what will you use? So, as a programmer, how will you switch from switch to a let's say as your application is running in the normal world, how will you switch from normal world to secure world? So let's say you're writing this C code. Okay, you're writing the code, you want to switch from your application to the secure world, do something, come back. How will you do that? So the answer is here. Is there anything on this slide that you can use? You want to switch, say, from the normal world to the secure world. So for that, what will you do? You have to call the monitor. You cannot switch yourself. Like you cannot change this bit, right? You cannot. So what? Currently the NS bit is 1. You want to change it to 0, and then you have to start. You want to start something. You want to start an TA application, trusted application. And so what will happen? Yes, SMC basically. So SMC is the answer. So SMC is also going to cause an exception only, but you can use the SMC instruction. Although what I said is not completely true, and like so this you can do only from the kernel. Okay, so you can call a SMC instruction only from kernel, not call basically. You can run a SMC instruction only from basic, not kernel, I should say, but from a privileged software. No, no. You don't have to program the monitor. You're going to write your application. You are writing your application, right? And your application is, say, this Armory application, which we are showing here, is running here. That application is going to use some APIs. Okay, that application is going to run some APIs, but and you're not at all going to change the monitor. The monitor, of course, you're not changing at all. It's some software. It's there in the secure world. You cannot change it. It should not be changed. Okay, it's not going to be changed. You are writing your applications and OSs here. The question what I was asking was that if you're running in the normal world, if you are in the normal world and you're writing your code in the normal world, then how will you change from normal? How will you go from normal world to secure world. So you can use the SMC instruction. If you write a SMC instruction in your program, it is going to cause an exception. That exception will be caught by the monitor. The monitor will see the arguments to the SMC instruction. It will check that okay, you are so it will check okay, the NS bit is 1, non-secure, and this request is to change from normal world to the secure world. So it will save the context of the normal world and start the secure world. Exactly. So you can switch from the normal world to the secure world using the SMC instruction called in the called in the normal world. That is absolutely right. There is only one catch, and which is this, that the ARM documentation, if you will look at the ARM documentation, then it says that the SMC instruction can only be executed in the by a privileged software. So SMC is basically a privileged instruction. So you cannot write a normal C application. uh, I mean, of course, what I mean to say is that you cannot write an application and run it in the user mode and write a SMC there, and that will not, that will actually lead to so your program will basically not be able to run, because the SMC is a privileged instruction, and your that privileged instruction can only be executed by the privileged software. So what does that mean is that only if you are writing an application, so if you're writing such an application like Armory here in this case, the Armory application will be running here in your normal world. The Armory application is going to have to request the OS. So it's going to like make a call to the OS that, hey, I want to switch to the secure world. Then the OS is going to make a SMC call on behalf of this Armory application, and then it will switch to the monitor mode. And say if the application wants to pass some arguments to the secure world, then those arguments will also be passed via the OS. Not as administrator or a root user, you can only run it in the OS. You can only run it in the OS. So not user. So the administrator or root are still running as users on your system. You can only run the SMC instruction, like even if you write a program, and even if that program has the privileges of the root user, and you cannot write a SMC instruction in that, and it will not execute the SMC. But if you write this SMC instruction, if you go and change your Linux kernel, and if you write an SMC instruction there, that will work. That will be, with that you will be able to switch to the secure world. Of course, you will have to like call with the correct arguments and so on. For that, you have to look at the SMC calling convention. I mean, that's a bit more detail, but the point to note here is that if you want to switch from normal world to the secure world and vice versa, it is true even from for this side. It is true, the same is true even for this side. The trusted applications here cannot make a SMC directly. They have to ask the OS. So if you want to switch from normal world to the secure world, there is you can, so that is enabled in these two ways. One is a programmatic way. One is through programming. You can add these instructions in your OS code, and then the OS is going to change the mode. Basically, the OS is going to call this SMC instruction is going to cause an exception that will be caught by the monitor. And as the application developer, you can call the API provided by the OS here, and this you can call this API, and then you can using this let's say here your OS is say providing a system call API, which is say call TEE. So in your application, you will use call TEE. You will pass your arguments. Then when the OS gets called with this system call, it is going to uh, make it is going to have their SMC instruction, which will which will cause exception, which will be caught by the monitor, and the monitor will switch control, which will switch the world from normal world to secure world. Is that flow clear? How you will switch from your application running in the normal world to the secure world? Okay, okay, so that is great. Okay, so the ARM trust zone has these two different worlds, normal world, secure world. Here, now we are going to look at that what guarantees do we get by running in the secure world? Like how is it beneficial at all? And what we have looked on this slide is that how we can switch from normal world to the secure world and vice versa. Okay, so we do that. For that we have to use we can use the SMC instruction, but that instruction can only be executed from the OS. So as a client, so as a user application, you can leverage services of the OS to make this SMC call. And then when the SMC instruction is executed, then the monitor catches the exception, and then it changes the NS bit, where the NS bit basically signifies that in which mode your processor is running, whether it is running in the secure world or the normal world. And the NS bit equal to 1 indicates that your processor is running in the normal world. Now we are next going to look at that how does this separation between the normal world and the secure world provides you these guarantees such as confidentiality and integrity of um, the application running in your secure world. So this NS bit extends beyond the chip. What does that mean is that the NS bit is not only used by the processor to this is not only used by the processor to find out that which mode it is executing in fact this NS bit is passed on to other components on your chip. For example, the caches, the boot ROM, the SRAM, the memory controllers and all. So the non-secure bit which we just saw, which indicates the world in which your processor is running, whether your processor is running in secure world or normal world, is used not only by your processor to keep track of the world in which it is being run, it is also being passed by the processor to the other components in your chip, such as the caches, the RAM, memory controllers, etc. Now, why is it being passed? Because you want to enforce some, you want to basically uh, propagate this information there, that the processor is basically propagating some information to these components. So let's say the processor is running in the secure world, then it is going to tell to the caches that, hey, I'm running in the secure world, and then also to the memory controller that I'm running in the secure world. Now, similarity to the DRAM. So what happens is that the memory in your RAM is actually configured to and divided into these two parts. Okay, so this is configuration at the memory level. So your memory in your system, let's say if your system has this 4 GB of RAM, then your memory is configured such that some part of the memory belongs to the secure world and some part of the memory belongs to the normal world. Okay, so your memory is divided between the two worlds. How much memory to give to which word, I think that's like configured. Okay, we're not going to worry about that. So your memory is divided between the two words, so that is why this information is being propagated here. Because if your os if your processor is running in the secure world, uh, let's say uh, if a processor is running in the normal world, then then the process should be able to access only the non-secure memory or the memory belonging to the normal world. So that's why this information is being propagated here, because we are because we want to ensure that if a normal world application is running on the processor, then that application cannot access the secure world memory. And this is enforced by the memory management unit. Okay, so let's say this is your CPU core, although at a time this can run only in the secure world or the normal world. And but we are here showing with these two different colors, that say the green color is let's say for the secure world and the red color is for the normal world. So when your CPU core is running at that time, when it passes, say some let's say your process is running on this on your processor, on your CPU core, and it is trying to access some memory. So there is some, say, load instruction. So the load, after the load instruction, it is along with the, when there is a load instruction, it has some address, the load address, the address from where the content should be read. So now that address is what? The address is actually a virtual address. It's an address inside the process, which is a virtual address. So the process, because of memory virtualization, okay? So that virtual address is passed to the MMU along with the bit value, the NS bit value, and it is passed here as the extra 33rd bit along with the VA address. So assuming that the VA is of 32 bit, I mean the virtual address is 32 bit, you pass one more bit information, which is NS bit value, which is indicating whether your processor is running in the normal world or the secure worlds. So let's say if your processor is currently running in the normal world here, then you will pass value here 1. So if NSTID equal to 1, then it forces the NS bit to 1, and then this value is being passed here. Okay, so you're passing this value here. Now what your MMU is going to do? MMU is the memory management unit. So what does the memory management unit does? The memory management unit is going to actually does do the page walk. So there's something called page tables in your which are in your system, right? So what does the page table do? The page tables are has the mapping, basically the page table maps your virtual memory to the physical memory. So this is the mechanism which is enabling the isolation between the processes, the memory virtualization. Now here, what the MMU does is that if you give it a value 0, then it is going to uh, select the page table for the uh, normal world. And these page tables can only translate your virtual address to a physical address belonging to the normal world memory. Okay, I hope that is making some sense. So basically, your MMU, when it sees the value bit 0 here, it is going to page walk these non-secure page tables. Okay, it is going to page walk the normal world page tables and translate the virtual address to the physical address. So in this way, when your processor is running in the normal world, it will be forced to access only the physical memory which has been configured as the normal world memory. It cannot access the secure world memory, and that guarantee is provided by the hardware, because the hardware here, the memory management unit, is aware of the fact that the CPU is currently running in the normal world. So the page tables that it has to use for the translation, the address translation, it has to use the normal world page tables, which are mapping the virtual addresses to the normal world physical addresses. I hope that makes some sense. Is there any question? Okay, so that's uh, and along with that, this NSID bit information is also actually stored in other hardware structures, such as the translation look-aside buffer. What is a TLB? A TLB is a hardware structure which is basically used to cache the virtual address to physical address mapping. So because the virtual address to physical address translation, for that you have to walk the page table, and the page table accesses can sometimes like basically that is a costly operation. Like it can lead to 4 to 5 memory accesses, and a single memory access to the RAM, it's in itself is a costly operation. So 4 to 5 memory accesses will be required if you want to even say load one word of memory from your, even if you want to say, even when you say load X, that will lead to in effect 6 memory accesses. Consider, assuming that 5 memory accesses are used to walk the page table. If you don't understand this detail, it's okay. Don't worry about it. That's not needed. But we have a TLB structure, translation look aside buffer, which basically is going to cache the virtual address to physical address translations, so that uh, the hardware can quickly find out that okay, I'm trying to access this virtual address, where is this located, and then it can just go directly to this physical address and read from there. Okay, so but here along with this mapping, it also stores here the NS bit, which signifies that which mode this for which mode this virtual to physical address mapping is valid for, whether this mapping is for the normal world or the secure world. And this information is very important to be kept here as well, so as to uh, keep the memory of the normal world isolated from the secure world. So in this diagram, actually, the red color is representing the secure world. And what it is showing now with this arrow is that even though the normal world should not be allowed to access the secure world memory, we can allow the secure world to access the normal world memory. And for that, we can map the memory of the we can allow it we can have a mapping for those memory addresses through the page table, so it can have these edges to the non-secure memory. What it is saying basically is that in ARM trust zone, the normal world cannot access the secure world memory, but the secure world can access the secure world memory and also the normal world memory. Basically, the secure world can access any location on the RAM. However, your normal world can access only the memory which belongs to the normal world. That's all. And even if you did not understand these two, three slides, what it is showing here is how this memory isolation is implemented by ARM Trustzone. So how does ARM Trustzone enforces that the normal world cannot access the memory of the secure world? Because that's very important if you want to isolate the softwares running in these two different worlds. Okay, so if you want to isolate these two words, what do you have to? You have to enforce that the OS which is running in your normal world cannot access the memory of the code which is running in your secure world. So that is enforced here in this way. Uh, these were the details basically. And similarly, we have even when you're storing the uh, even when you cache some data in your caches, at that time also along with the cache line data and the tag, you will store the ns bit. So all of the hardware structures, all of these hardware's components are made aware of this ns value. Okay, so as we saw here, the ns bit extends beyond the chip. So the ns bit value is propagated to all of the components, and all of the components are going to enforce this isolation uh, between the normal world memory and the secure world memory. And they are going to enforce that when the processor is running in the normal world, it can access only the normal world memory which has been pre-configured. So it is pre-configured when your system starts booting, right? At that time it is configured. So it's like a boot time configuration. And basically provided as in the configuration. You can say, okay, address in my RAM from address 0x000 something to address 0xf 000 belongs to my secure world, and beyond that is my normal world memory. So you have to specify that during the boot time, and once you specify that, then your this entire circuitry is going to take care that that is enforced at runtime. So the normal world cannot access the memory which does not belong to it, while the secure world can access any memory on the RAM. So that's the memory management. Hmm. And similarly, the devices are also made aware of this bit, where the secure world and the non-secure world, and some of the devices can be configured to run only uh, when the processor is running the secure world. For example, here this GSM modem is being configured such that only when the secure world is running here, only at that time this device can be accessed. If the normal world tries to access this device, it will not be able to access this device. So we can configure the peripherals as well, uh, and we can pass this ns bit there also. Is there any question? Okay. So now about the interrupts. How are interrupts handled in now in this setup? So when an interrupt comes, then it is actually routed to the monitor first. Whenever any interrupt is going to come, it is going to be routed to the monitor first. In earlier, when we had this simple, when we did not have this normal world and secure world concept, if any interrupt came, then it was passed to the OS, the normal world OS. Now, if any interrupt comes, it is going to be passed to the monitor. Okay, and then your monitor has been configured, and based on the interrupt, it is going to decide whether to pass that interrupt. Like it can, like the interrupt, it will have this table. Okay, and it will look at the interrupt type, and this table will give it information that who should service this interrupt. So the interrupt can either be for the monitor itself, so maybe the monitor should service that interrupt. If the monitor, if that interrupt is for the normal world, then it is going to pass the interrupt to the normal world. And if the interrupt is for the secure world, then it's going to pass the control to the secure world. So when you execute a SMC instruction here or here, at that time, that SMC instruction is actually causing an exception. It's calling causing an interrupt, and that interrupt goes to the monitor, and then the monitor will look that okay, this interrupt was generated by the SMC instruction, and then I have to change the word, and then it will look at the current value of the NS bit, and then it will change, save the context of the current word. It will restore the context of the other word, and then it is going to change the value of NS bit. And that's how word switching works in ARM Trustzone. And of course, at a time, your processor runs in only one word, and your processor runs in time sliced manner between these two words. So a little bit detail is just that there are these interrupt vector tables. There are different tables in your all of these three components. Here there is a normal world interrupt vector table for your OS in the normal world, secure world interrupt vector table, and then your monitor has its own monitor interrupt vector table. Now our entry in the vector table is going to be is it's either a code, it's like a simple code sequence usually, or it is like a address of the interrupt service routine. It passes the control based on the interrupt type. You will access some interrupt entry. Okay, you're going to go to that interrupt entry into the table, and then the interrupt entry will have say some like address of the interrupt service routine, and when that service routine will be called, and then when that service routine is going to service this interrupt, and then it will go back, return back. So this was so this is all about ARM Trustzone. And so the ARM Trustzone typically can have an entire operating system in the secure world, and like these are the examples of the secure operating systems: Qualcomm's QSSE, Trustonics NIBI, Samsung Knox, and Node. So these are the secure operating examples of the secure operating systems, and these secure operating systems will be running in the secure world. So usually these secure operating systems are like less complex compared to the rich operating systems. Okay, and it's saying here that the secure OS could be tightly coupled to the rich OS, so that a priority of a task in the rich OS gets mapped accordingly in the secure OS. So there can be some like there can be some sort of like you can basically um, develop these two OSs so that they understand each other, and so that will enable us to do some more uh, complex tasks, such as you can pass the priority of a task from rich OS to the secure OS, so that that application get executed first. So with that, we have looked at the trusted hardware ARM Trustzone. So we started our discussion with that we need trusted execution environments because our application is running a sensitive code or working with sensitive data, and we do not trust our system, and we want to have a secure region where we can run this application, and so that we have confidentiality and integrity, and that is provided by the uh, secure hardware such as this ARM Trust Zone. So now maybe you can tell me, if you have a secure, if you have a sensitive application, where will you run that application so so that it is secure in with respect to ARM Trust Zone? Where will you run your application? So we started here, right? We started here. We said, okay, this is our sensitive application which is running here, and this is an untrusted system, and we do not trust the system. So that's why we are going to run it inside a trusted execution environment. Now, I'm asking you, where are you going to run this application now? Yes, we're going to run in the secure world. And where exactly in the secure world? So if it's an application, it will be run here, secure world, user mode. Yeah, so it will be run here in the secure world user mode. Now, uh, maybe, do you have any questions? Is there any question? Okay. What is the advantage of secure world accessing pages that belong to the normal world? Yeah, so there can be different reasons for that. So one of the reasons can be it gives the secure world uh, so it enables the secure world to introspect the normal world. Basically, the the secure world can they scan the memory of the normal world, and it can try to see if there is some malicious binary or something. So it can try to like, if it has access, so it has access to the entire memory, that it can enforce some things. It can try to look at the memory content and detect if there are any viruses on your system or not. That's one thing. Another thing is that it it helps to like, if you want to pass some information from the normal world to the secure world, then like basically if you want to pass some data from the normal world to the secure world, then the secure world basically can go and read it directly. You just pass the pointer. You just have to pass the pointer to the memory, and since the secure world has the access to the normal world memory, it can go and directly read it there. So there would you would not have to copy that. That's there. Also, there can be other reasons as well, of course, but these are the two main reasons which are coming to my mind right now. One is that the secure world, if that is able to access the normal world memory, that it can check the content of the memory to say check what is stored in the memory, and then it can try to find if there are any viruses or anything. And another is that if it wants to read some data, then it can go and directly read it without the need of it being passed from the normal world to the secure world. So not only the memory, basically the normal world can access everything. It can access even the registers, and so it can access all of the components. The restriction is on the normal world. Say it cannot access something, but the non it cannot access say, some device or some registers or memory. But you can access almost everything from the secure world. Yes, so this architecture can be useful to monitor the normal OS for a malicious code as well. That's absolutely right. So yeah, when we were discussing that you have booted up securely, but then afterwards, if the OS is changed, then what? How can it be detected? Yeah, so here the secure world can do that attestation basically. Now the secure world can do the runtime attestation. So it can periodically take a snapshot of the normal world memory and send it back to the client. Okay, so periodically it is going to take a snapshot of this memory, send it back to the client for verification that, hey, currently this is the memory and this is where the kernel code is located. So this is what is being run right now. So then in this way, it can do a runtime attestation. I hope that makes it clear. And is there any other question? So yeah, similarly, when we were talking about TPMs earlier for the secure boot, we can use this trust zone for also secure boot. In fact, the trust zone, what the boot process, yeah, I forgot actually to mention. How does the booting happens is that first the monitor is going to be started, then the monitor start the secure OS, and afterwards it's going to start the when the secure OS has started and say the application or something, then it is going to pass control back to the monitor, which is then going to start the normal world. So that's how it works. Mm, see if there are any more slide. Oh yeah, it's there. So the secure boot. So why do we need secure boot? Because the attacker may replace the flash software with a malicious version compromising the entire system, right? So we need a secure chain of trust, and we are starting from the root device, root of trust that cannot be easily tempered. So this we have already discussed. What is secure boot? Why we need secure boot? How we can do secure boot? Now let's see how we can do it with the uh, ARM Trustzone. So here the CPU boot will happen. The CPU is going to uh, check the ROM bootloader. Okay, it's going to check the ROM bootloader, and then sorry, this is the boot sequence. So the CPU boot happens. It's going to start the bootloader, which is stored in the ROM. The ROM is going to start this. So the bootloader is going to now start the monitor. Okay, and the monitor is going to start the TEEOS, and once the TEOS has started, then it is going to pass control to the of course via the monitor it will pass control to the OS, rich OS here, and then the rich OS will boot up. So this will be the boot sequence, and so this will be the boot sequence, and then now the attestation will happen in this way. And now your root of trust here is the arm trust zone. And because your attestation will be starting from the arm trust zone. Okay, and this is the chain of trust. So you trust here some hardware, in this case the arm trust zone, and earlier we saw with TPM. So you inherently trust some component, okay, such, and that is the root of trust, such as a TPM or trust zone or on chip ROM, etc. And then that component is then going to uh, so what there we were doing was actually attestation. We were generating a proof, but we some not here what we are doing is just a secure boot. That was attestation, and this is secure boot. Now how are they different? So it will, so how are they different is that that was like a detection mechanism. So you were storing this values, like which what is being started next, and then you were passing this back to the client for verification. Here it's different in the sense that it is uh, detection is not going to be happening on some other, at some other verifier. It's happening here only. So first when the ROM here, the, let's say this inherently secure component is starting, it is going to verify the integrity of the bootloader. So it's going to take a say hash of this bootloader, and it is going to check whether this matches with the correct hash of the bootloader or not. Then this when once this component has verified this, it is going to give control to this component. Then this component is going to compute hash of the next component boot chain, secure OS. Now the secure OS hash will be taken by the bootloader, and it will have a hash value known to it uh, from like ahead of time, which it is going to take and compare against. And if it finds out that the value that it has computed now matches with the value what it knows, then it is going to pass the control to the secure world. Then the secure world is going to start these trustlets, which are like the trusted applications. And when it starts a trusted application, it, but before it started, it is going to take hash of that binary code and verify that it is actually matching, and then only it will start. And then finally, when the secure OS has also finished finished like the boot up and setting up, then it is going to check the hash of the rich operating OS, rich OS, and it is going to compute the hash of this, and then it is going to verify it with the known value of the hash. And if the values do not match, then it is going to uh, like stop, the boot won't happen. Okay, the boot up will fail. So the boot up can fail at any point, and the boot up will start from the lowest layer which you trust, the root of trust, which can be either your TPM, which can be your trust zone, hardware, or like the on chip ROM here. So this is inherently secure, means you know that it is secure. It's like a trivially secure, you know it's secure, it cannot be tampered with. And then you check the signature of the next component in the boot chain by computing the hash of that component and checking it against a known value. Then you pass the control to the next component only if that component if you are able to verify that it is correct. And then this component is going to check the integrity of the next component, and so on. So this is a secure boot. What we were discussing earlier was generating a proof of this, and this is like if the check fails at any point of the time, then the boot will stop. And this is called a secure boot. This is just secure boot. That was secure boot attestation protocol. So that was the difference. And what you were mentioning now here is absolutely right, that once the boot up has happened, afterwards also the secure world side can monitor the memory of the rich operating system or the other applications on this system, because it has a view of the entire memory of the system, and it can basically attest any memory. So it can read any memory, so it can actually, you're right, this is also widely, this is one this is also the application of TEEs here, is that they can I mean it is widely used to attest the memory. So since it has a view of the entire memory, periodically it can take a snapshot of this memory and then it can send it to, say, some verifier, or it can verify itself also here. So that will be runtime, that will be the attestation of the OS when it is actually running. I hope that clarifies uh, that question, and if there are any other question, then please let me know. Okay, so if there are no question, then or if there are any, then please feel free to put them in the chat box. What we are going to do now is we're going to stop for 10 minutes, and after that we are going to look at Opti. Opti is an open source implementation which allows you to leverage Trustzone. So you can uh, if you want to work with the Trustzone, then you can use Opti, and then you won't have to worry about the details, too much details, or it will basically make it more easier to do development in the Trustzone. So next we are going to look at the Opti framework, and just simple Opti app. We are going to look at that where these trusted applications are stored, and we are just going to make some change into our trusted hello world. We are going to look at a hello world example, client application, and also the trusted application, and then we are going to change some value and compile and see it works. That's all. It's very simple. It's nothing complicated at all. It's very simple, and hopefully that will help you like some at some point when you get started, if you want to work with ARM Trustzone, and if you want to get started. So let's stop for 10-15 minutes so that we can meet at 5:45, and then we will look at this short demo, and then after that we will wrap up for today, because I think it will be 6:30 or so after that, and then we will wrap up for today. So let's meet at 5:45 now.